Hello, everyone. Welcome to section 10.4. This section is on the algebra of matrices. So we're going to be talking about when we have matrices, how we can sort of add, subtract, and multiply them. That's what this section is going to be about. So to get started, first we should talk about when two matrices are equal. And they're equal kind of when you would expect them to be. So two matrices are equal when all of their entries are equal. That's kind of what you would expect, right? So if you had the matrix like 1, 2, 3, 4, that's going to be equal to the matrix 1, 2, 3, 4. But if you have the matrix 1, 2, 3, 4, that's not going to be equal to the matrix 1, 3, 3, 4, right? Because they differ on an entry. There's 2, there's 3, they're different. So matrices are only equal when all their entries are equal. That kind of makes sense. So now that we've gotten that out of the way, let's talk about adding and subtracting matrices. So if you have two matrices, of the same dimension, you can add and subtract entry-wise. So I'll explain what that means in a minute, but it's very important that you have matrices of the same dimension. So for example, if you tried to do something like 2, 1, 3, 4 minus matrix 1, 3, 5, 6, 1, 7, for example, you can't do this. This doesn't make sense because we have a 2 by 2 matrix here. There's 2 rows and 2 columns, and this one has 2 rows and 3 columns. So this is a 2 by 3 matrix. They're not the same dimension. You can't subtract or add them. Okay, so this doesn't make sense. It's impossible. Okay, they're not the same dimension. Okay, but if they are the same dimension, we can add, subtract entry-wise. And what that means is if we have two matrices, like maybe we have something like 1, 3, -7, 2, 6, 0. Let's say we want to add it to 3, 5, 2, -2, 0, 1. Okay, if we want to add these together, all we do is we just take the first row, first column entry, and we add it to the first row, first column entry of the other one. And then we do the same thing with this one and this one, right? So we just kind of add entry-wise. We get 1 plus 3. Those are the two circle ones in yellow. And then we get 3 plus 2. Those are the two ones I circled in blue. And then we would get, -7 plus 5, right, from the entries right below the yellow circles. And then we get 2 plus -2. And then lastly, we'd have 6 plus 0, and then 0 plus 1. And then if we go ahead and simplify this a little bit, I think we end up getting 4, 5, -2, 0, 6, and 1. And then if you were subtracting matrices, you would just subtract all the entries from each other instead of adding them. So pretty straightforward. Unfortunately, this is, well, it's not the simplest because what we're about to do is also fairly straightforward. But it's one of the simpler things we can do with matrices, which is nice. The other simple thing that you can do with a matrix is you can do what's called a scalar product to it. So what that means is if you have a number a real number of some sort, let's call it C. This is what's called a scalar when we're talking in matrix land. You can multiply or scale, hence the name, a matrix A by C, just by multiplying each entry in A by C. So for example, let's say RC was like 1/2, right? And let's say we wanted to multiply or scale 1/2 by the matrix 2, 3, 10, -8, right? All we would do is we just multiply each of the entries by 1/2. So we would get 1/2 times 2, 1/2 times 3, 1/2 times 10, and 1/2 times -8. And then we would just simplify. So we get 1, I'll use this as 3/2, and then 5 and -4. So that's scalar multiplication, also called a scalar product. Also fairly straightforward, which is really nice. So let's talk about some general properties of addition and scalar multiplication with matrices. And of course, all the properties that hold for addition are going to hold for subtraction as well. Okay, so let's say if we have some matrices, let's call them A, B, and C. And we also have scalars, C and D, then the following properties hold for these operations, right? So in particular, we have commutativity of matrix addition. So what that means is that if we have A plus B, we can swap them around and we can write B plus A. That's totally fine. They can move around. That's okay. They also have associativity of addition. So if we wanted to do A plus B, so add two matrices together, and then we wanted to add C to that, that's exactly the same thing as doing B plus C first and then adding A. So addition of matrices is associative. What's also associative is scalar multiplication. So if we did C times D times A, so if we scaled A by D and then scaled it by C, that's exactly the same thing as doing C times D and then just taking that and scaling A by that. And then lastly, we have the distributive properties. So in particular, if we have the scalars C plus D, and we have that product and we scaled that so we scaled A by C plus D, that's the same thing as doing scaling A by C and adding it to A scaled by D. So you can kind of distribute. Similarly, if we have a scalar C times a matrix addition A plus B, that's the same thing as doing as scaling A by C and adding it to B scaled by C. So we can kind of distribute that way as well. Okay, so addition and scalar multiplication of matrices is very nice, fairly straightforward. It's defined entry-wise, so it works pretty much the way you would expect it to. Unfortunately, there is one particular very common matrix operation that's not so straightforward, and that's matrix multiplication. So you can indeed multiply matrices together. It's just a little funky. So if A is an M by N matrix, so M and N here are numbers like 5 and 3 or whatever, and B is an N by K matrix, then we can multiply them. So it's very important that these two things match up. And we'll see why in a second. So let's say we wanted to do A times B. The way we would do that, actually, let me write this here. Let's say we had the matrix A. And I'll fill in some things in a minute. We had the matrix B here, so we're multiplying them. And then this is what's going to get spit out. If we look at some row of A, so let's say it's got some entries like this. Let's give this row a number, but just an arbitrary number. So let's just call this like the ith row. So it's like maybe we're looking at the second row or the fifth row or something, but whatever row we're looking at, it's the ith row of A. And let's just give it some values like A, B, and C. And then we're going to look at a column in B. So again, let's just give it some arbitrary numbers. So this will be like the jth column, right? So like the third column or whatever. Now let's give them some values like X, Y, and Z. We use the ith row of A and the jth column of B to figure out what the ijth entry of A times B is. That is, we're using the ith row of A and the jth row of B to figure out what the entry in A times B at row I, column J is. Okay, and in particular, that entry is going to be A times X plus B times Y plus C times Z. And this works for if you have more entries. So if you had like if you had 4, it would be A times X plus B times Y plus C times Z plus D times W. So what you're doing here is you're taking your row, the first one, and you're multiplying it by the first one in that column of B, and doing the same thing with the second ones. And the same thing with the third ones, and so on and so forth. And once you multiply this and once you add them all up, that's what goes into here, into that ith row jth column entry of A times B. So this is really confusing, I'm sure. Matrix multiplication is not nice. So let's go ahead and take a look at an example, and let's try to get a feel for it in maybe a more concrete setting. So let's say we wanted to multiply 2, 1, negative 3, 4. And let's say we wanted to multiply it by 5, negative 1, 7, negative 2. Now, remember my note that when you're multiplying matrices, their dimensions have to match up in a very specific way. So this is a 2 by 2 matrix, right? And this is also a 2 by 2 matrix. When you're multiplying two matrices together, you really want to make sure that this number here and this number here match up. And in this case, they do. So we can do this matrix multiplication. Okay, but as far as actually doing it goes, let's take a look. So here's the way I think about it. I start with the first column of the second matrix, and I multiply it, or not multiply it, I combine it, is a better word probably, with the first row of the first matrix. And so what we end up doing is this 5 is going to end up being multiplied by this 2, and this 7 is going to be multiplying by this 1. And so that will be the first, so the very left top entry of the new matrix product. So it'll be 2 times 5, so that's the blue, plus 1 times 7. Those are the things we circled in red. Okay, so that's our first entry. And then we can take this first column again, and we can do the same thing to the second row. And so the second row starts with a -3, so we'll get -3 times 5 this time. And then we'll get a plus 4 times 7. Okay. Okay. So now we do the same thing, but with this column. So we look at this column and we're going to combine it with this row first. This is to fill out this entry right here. And the way we're going to do that is we're going to take this -1, it's going to multiply by this 2, and then to that we're going to add this -2 multiplied by this one right here. So when we do that, we get 2 times -1, so those are the blue, plus 1 times -2. And those were the things we circled in red. And then we do the same thing for the other row of the first matrix. And so we get -3 times -1 plus 4 times -2. Okay. Okay. So now we just go ahead and simplify the entries. So we get 2 times 5 is 10, plus 7 is 17. And then for the entry below that, -3 times 5, this can be -15, plus 4 times 7 is 28, if I'm not mistaken. And I think that works out to be 13. And then we get -2 minus 2, so this can be -4. And then we get -3 times -1, that's +3, plus 4 times -2, that's going to be -5. Okay, so that's multiplying some matrices together. Let's go ahead and take a look at another example, just so we can really solidify things. What if we wanted to multiply some maybe different shaped matrices? Let's say we had like 1, 4, 3. So let's do like a 3 by 2. So do -2 and maybe 0 and 0. And let's say we wanted to multiply it by maybe 5, 6, 6, and let's just keep it like that. Okay, first we need to ask ourselves, does this operation make sense? So we have, here we have 2 rows, 3 columns. So this is a 2 by 3 matrix. This is 3 rows, 1 column. So this is a 3 by 1. And if you notice, we have a 3 here and a 3 here. Those match up. That looks good. We can do this. All right, so let's go ahead and do this matrix multiplication. So there's only 1 column here, so we only have to do this kind of once. But we're going to take this column and we're going to combine it with this one right here first. And so when we do that, we get 1 from the first entry times 5 from the first entry of the second matrix, plus 4, the middle entry from that row in the first matrix, times 6, the middle entry of that column in the second matrix, plus 3, so that last entry in that row, times 6, which is the last entry in that column. And we need to make this a little bit bigger. And we do that for the other row. And so we get -2 from that first entry in the row times, times 5, first entry in that column, plus 0, the entry in the row, times 6, the entry in the column. And then again, we get 0 times 6 from the last entry in the row and the last entry in the column. And then if we simplify this, I think, so we get 5 plus, what's that, 24. So we get 5 plus 24 plus 3 times 6 is 18. And then we get -10 plus 0 plus 0. So this is going to be, I think 5 plus 24 plus 18, I think that works out to be 47. And then we get -10. All right, cool. So that was that matrix product. Maybe let's do one more example. Let's say we wanted to do 5, 6, 6. And let's do this times 4, 8, 3, 7, 7, 0. Okay, first, before we do this matrix product, let's check to make sure that it makes sense. So this thing has 3 rows and 1 column. So this is 3 by 1, just like last time. And then this has 2 rows and 3 columns. This is a 2 by 3. And if we look at these 2 numbers right here, they don't match up. So this is impossible. Got to be careful with that. Okay, so that's matrix multiplication. It's kind of tricky to keep track of things, but I'm not going to lie. This is one of the things where genuinely, if you do kind of practice it, it does start to make a lot of sense, and it does start to become a lot quicker. You just go boop, 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 boop. Eventually, you'll get much faster at it if you just practice it. It's gnarly now, but trust me, it will get easier. But before I send you off into the big wide world of matrix multiplication, there is a warning I have to give you. It's even bigger than worrying about the dimension, in my opinion. A times B is not the same thing as B times A. So even if both A times B and B times A make sense, so if you can, like, the dimensions match up, they aren't necessarily equal. Right? Matrix multiplication is not commutative. So just to kind of really like hone in on this point, our first example of matrix multiplication we had 2, 1, -3, 4 times 5, 7, -1, -2. And I think we found that that became 17, 13, -4, -5. Okay. So let's go ahead and take a look at what happens when we swap these two. So let's go ahead and do the matrix multiplication 5, -1, 7, -2 times 2, -3, 1, 4. These are still both 2 by 2s, right? So this multiplication still makes sense, right? So we're still good to go. But let's go ahead and do it out and see what happens. So now we're looking at this column, and we're going to combine it with this row. And first, we're going to look at 2, and we're going to multiply it by 5. And then we're going to take -3, and we're going to multiply it by -1. So that becomes 5 times 2 plus -1 times -3. And then if we do that same thing, but to the bottom row, we get 7 times 2 plus -2 times -3. And then we do the same thing, but now with this column, multiplying it by that first row, we have a 5 times 1, 1 came from the column, and then a plus -1 from that row in the first matrix times 4 from the column in the second matrix. And then for the next entry, we do this to the bottom row. And so we get 7 from that row times 1 from the column, plus -2 from the row times 4 from the column. Okay. So now, if we take a look at this, so 5 times 2 is going to be 10, and then that's going to be plus 3, so that's 13. And then in the entry below that, we get 7 times 2 is 14, plus 2 times 3, -2 times -3 is going to be positive 6. So I think that works out to be 20. And then we get 5 times 1, so that's 5, plus -4, so that's going to just be 1. And then we get 7 plus -8, so it's going to be -1. That's totally different. Because remember, when we did the other way, we got 17, 13, -4, -5. That's not equal. So the order in which you do matrix multiplication matters. Make sure you remember that. It's very important, especially if you keep going on to, say, linear algebra, linear analysis. This point will come up. And if you don't remember it, it will screw you over. Matrices and matrix multiplication, it's out to get you. Don't let it get you. Anyway, some of this stuff can be pretty hairy and kind of confusing. And as always, let me know if you have any questions at all.